As you can see from the title, I'll be talking about minimum propulsive power and EEDI regulation. So it's in a way it's very related to the last presentation that we heard before lunch. I'll be going in a bit more details there. Now, how do I start this? Here we go. Well, I guess all of us pictured that this EEDI conference would happen under happier circumstances, maybe. Personally, I had this idea of coming to London one last time before Brexit without talking to customer officials and so on, of having a pint at the club, of meeting colleagues and friends, and of strolling around Trafalgar Square. But as you all know, things turn out to be different. Not necessarily bad in my case, but different. I am today talking from home, which is on the small island north of Gothenburg on the Swedish west coast. My family and me have been on this island for weeks now in kind of practical or almost complete self-isolation. We've just had a baby daughter. I'm on parental leave. The weather is great, and as you can see from the pictures, there's plenty of other things to do in between changing nappies, that is. So yes, it's a nice time out here. The island and the limited bandwidth are also the reason why I choose to turn off my video today, so apologies for this. Now, normally, if I'm not on parental leave and sailing, I commute to Gothenburg every day, where I work at SSPA. And I suppose that most of you have heard about this company, which started some 70 years ago as a model testing facility and has since expanded into a maritime consulting company, which much broader services. We are owned by Chalmers Foundation, the same foundation that owns Chalmers University, and our main customers are maritime operators, shipyards, designers, such like. And altogether, over the last 75 years in business, we've tested about 8,000 plus hull forms. But now, back to business and EEDI. Most of this we've seen in the previous presentation. So if EEDI and emissions practically limit your engine size upwards, IMO have also placed a regulation into place, or put a regulation into place, which ensures that your ship operations are still safe. It's this minimum power regulation. And this is to, well, avoid that you end up on a stormy night on a lee shore without sufficient power to get away. The full title of this guideline, which I'll be talking about today, is the minimum propulsion power to maintain the maneuverability of ships in adverse conditions. So quite a lengthy title for like 6-page document. And this IMO guideline about minimum power is an interim guideline. So this means it's not perfect and it's not final. And in fact, there's been a lot of criticism and calls to modify it. But nevertheless, to my knowledge, it's still binding at the moment. So there's a point looking into it. Now, broadly speaking, this IMO guideline gives you two different ways to show compliance. We've seen both of them a little bit in the previous presentation also. First, there's a simple level 1 assessment. This is a straightforward generic method, which is based on installed power of existing ships. This uses dead weight and ship type as the only inputs and then spits out a minimum power. And then there's the level 2 assessment, which is a bit more elaborate. This is based on individually calculating various ship resistance components and carrying out like a proper power prediction based on those resistance forces. Now I will today go through both level 1 and level 2 calculations and also discuss challenges and loopholes in those IMO guidelines. And for this, I will use the well-known KVLCC2 tanker as an example. Now, compared to smaller tankers like Aframaxes and so on, VLCCs are usually not critical in terms of minimum power, like in real life. I will nevertheless use a KVLCC2 today because it's open source. You can find a lot of information in the literature, and it might serve as a very useful benchmark case. So a bit out of sequence, but I'd like to show you some results first. If you carry out the simple level 1 assessment, you will find that the minimum power is slightly above 25 megawatts for the KVLCC2. If you carry out a level 2 assessment, it's around about 9 megawatts. So there is a significant difference between the two assessment levels there. Luckily enough, the simple generic method is conservative, but it's also very, very conservative for this VLCC, at least. So I would say that no serious ship designer would want to rely on the level 1 method, really. And yeah, we can take a closer look at the two methods. Here's just one slide about the simple level 1 method. Down here, top, can you see my cursor now?
Yes, we can.
Okay, good. So here in this box, this is really the level 1 assessment, which spits out a minimum power as function of dead weight, tonnage, and coefficients A and B. They are tabulated for various ship types. And if we assume that the dead weight of the KVLCC2 is about 300,000 tons, yeah, you enter those tables and it spits out 25.5 megawatts as minimum power. So this is what we've seen on the previous slide. It's very conservative, and yeah, there's a point of looking at the level 2 assessment also. This level 2 procedure is much more complicated, and I've tried to summarize it here in this slide here in this figure. This is really our roadmap for the rest of the talk. You'll also find this in the proceedings in a much nicer format here. I had to cut this into 2 parts, really, joined by the blue arrow here, because it wouldn't fit the landscape format otherwise. Now, the main assumption and starting point of the existing level 2 assessment, and this is really the key point here, is that your ship is safe and the engine big enough if you can maintain a certain minimum speed in headwaves or a headwind of a certain strength and corresponding waves. So what IMO effectively does is they reduce the safe maneuvering problem to a 1 degree of freedom problem, to a force balance really in the x direction of the ship. And then there's this minimum speed, or the minimum required ship speed of advance, as they call it, depends on the relative size of the rudder compared to the ship. And it varies between 4 and 9 knots, depending on yeah, ship parameters. And then IMO requires that you maintain this speed in adverse weather conditions, and they define those weather conditions as Beaufort 7 to 8, also depending on ship size. So now you've got the required speed, and then in the next step they work out resistance components here, calm water resistance, wind resistance, and added wave resistance, which you calculate separately. You sum this up into a total resistance, convert it into a thrust using thrust reduction factors there. Then you do a power prediction based on propeller characteristics. And out comes really like a power RPM calculation, which you can compare to your engine characteristics, or to your engine. First, you can check the engine size. Is it big enough to deliver this power? And then for ships with like rigid drives and fixed pitch propellers, you obviously need to check that the diesel engine can really supply this power at this RPM. We've also seen this in the previous slide, the engine diagrams that we've seen. We'll see them again here. And then hopefully your engine is big enough and it you don't bump into the torque limitation line and then you're fine, or well, maybe you're not. So this is really how this level 2 assessment works. And yeah, I will go through this a bit now, using this KVLCC2 as an example. Now, as I've said, the required ship speed depends on main particulars. It depends on ship length, LPP, on draft, beam, and it depends on rudder area and frontal and lateral wind areas. And depending on ship size, it's between 4 and 9 knots. For the KVLCC2, it turns out to be on the low end. It's 4 knots. So we need to make sure that whatever engine we choose now, that we can maintain those 4 knots in the adverse conditions. And adverse conditions, and this is a bit special about this particular IMO procedure, they're not defined as one single wave spectrum or wind condition. They're defined as a range of spectral periods, and I've plotted 3 of them here. So IMO says you need to be able to maintain the speed in John swap wave spectra with periods ranging from 7 to 15 seconds. You can see those 3 spectra within this range in the plot down the bottom, spectrum 1, 2, and 3. We will see them again and again in my presentation now. The blue one, spectrum 1, is the lower end of the spectral range, and the green one, spectrum 3, is the higher, the 15-second end of this range. So keep in mind, it's not only one power prediction which we need to make. Now we need to make sure that in all of those, that for all of those spectra between 7 and 15 seconds, we can maintain the 4 knots. Coming back to our roadmap, we've now worked the advance, the required speed. We've worked this one out, it's 4 knots. And now we can start looking at calm water and air resistance and calculate it at those 4 knots. Down the bottom here, you've got the equation which IMO gives for the calm water resistance. It's based on a form factor which IMO recommends to take from model tests. Well, they recommend taking it from model tests, but also give like a generic main particular based alternative to calculate it. At SSPA, we've done model tests with a 7-meter model, with a relatively large model of the KVLCC2 in our towing tank and calm water, and using this equation up here and the results from the tests, we end up with 126 kilonewtons full scale for the KVLCC2. If you use IMO's generic equation, you're slightly above it, about 6%, you get 134 kilonewtons. So now we've got calm water resistance. We can look at wind resistance, air resistance also. The IMO guideline gives this equation up here. And they also recommend taking the resistance coefficient CR from model test, which means wind tunnel test in this case. But they also, again, give like a generic alternative where they say the coefficient is 1. So based on model tests for the tanker, we get 307 kilonewtons, and again, slightly more for the generic expression. So so far so good. Now we've got those 2 resistance component. We still need the 3rd one, the added wave resistance component, and this one proves to be a bit more tricky. First of all, because the IMO guideline is not very specific how to determine it. They say it should come from tests in regular waves, but they don't really say how those tests should be carried out. And well, it's quite ambiguous. They also say, or it could come from an alternative method verified by the administration. So yeah, it's you don't really know what to make out of this. The second reason why it's very tricky to determine this added resistance in wave is because the model testing itself is not straightforward, and this is because the tests have to be carried out at very low speeds. You need to keep in mind this is 4 knots. Usually tankers are tested around 12 knots, 15 knots, so it's like a quarter or a third of the speed that we usually have. This means, first of all, you need to have a very wide base, or a basin, not really a tank, because as you go into your regular waves, your ship will start to generate its own waves from heaving and pitching. They will eventually meet the walls of the basin or the tank and get reflected back onto you. And at 4 knots, you need to have a very wide basin so that you can outrun this wave system before it interferes with you. So it's impossible to do those 4 knot tests in a tank. You need to have a basin, really. And then the last complicating factor is really that added resistance itself as a difference between tests and waves. And no waves is very tiny at such speeds, and you need to measure very precisely. So this here is what we've come up with at SSPA to measure added resistance in waves at low speeds. It's a modified soft mooring approach. You've got a schematic illustrating it here. You've got like plywood wings sticking out at deck level of the model. And then sort of a stiff wire towing frame around the model, which is connected to soft springs and a towing point on the carriage. So it's almost like a free sailing model test, but you tow it, and you use force transducers in the lines and the geometry of the setup to work out the resistance of the ship. The purpose of the springs is to dampen out any sort of violent jerks that you might have if you encounter waves. So if you do this, you can carry out very careful tests. You can determine the quadratic transfer function, or RAO, of added resistance. So wavelengths here, regular wavelengths here, and added resistance here. And now IMO says that you should integrate this transfer function with your spectra, like the 3 spectra or the full spectral range. And if you do this for our 3 example spectra, you get those resistance values here. And here down the bottom, I've plotted it for the full spectral range from the IMO guideline, 7 seconds here, upper limit 15 seconds here. And you can see that there's a sort of very shallow peak here for the spectrum number 2, somewhere in the middle, of around 840 kilonewtons. So this was our missing resistance component, really. So now we've got we can really work out our thrust, or almost. We still need to have the thrust deduction factor. I come to this in the next slide, but we can also have a quick look at the relative size of the resistance components. So in spectrum 1, which was the one with the highest added resistance, you see that the whole problem is really dominated by the green added wave resistance, like wind resistance in second, and then the calm water resistance, for which we've carried out dedicated towing tank tests, is really quite small compared to the other components. Now, IMO recommends to do model tests to work out this thrust deduction factor, and they're unfortunately, again, not very specific how to do this. It's again tricky because all this is at 4 knots. It's not the normal self-propulsion and resistance test that you carry out. It's very low speeds. And for VLCC2 tankers, I've plotted the thrust deduction factors and wake fraction factors, which we will also need later, from various sources in those 2 diagrams, which you can find in the proceedings. Now, there's a lot to say about those 2 plots, but the main point is that the IMO generic values, the red lines here down up the top, they're not necessarily conservative, and the choice of propulsive factor does have a significant effect on the outcome of the minimum power calculations. To illustrate this, I looked at 2 scenarios. I call them scenario A, which is conservative, and scenario B, which is optimistic. And based on those assumptions and with the resistance values from the previous slide, I've made some power prediction, which I can show in the next slide. So here finally you've got the required power as function of the spectral wave period. And to sail with 4 knots in spectrum 1, you need about 7 megawatts, slightly more for the spectrum 2, and then again less for spectrum number 3, so highest power somewhere here. And then these are 2 black dotted lines. There's scenario A, which is conservative, and scenario B, which is optimistic. So this year the difference is about plus minus 1 megawatt. So it's quite significant that you choose T and W correctly. Then here again, you've got the 25.5 megawatts from the level 1 assessment, and this is, as you see, it's literally off the chart. It's really conservative. Now we've worked out a power, but we still need to check that our diesel engine can actually provide those powers at the corresponding RPMs which come out of the power prediction. And this I've done here in this slide. You've seen this before. You've got RPM or engine speed here, and delivered power on the vertical axis. And here the green line is really the torque limitation line. You might remember this from the previous presentation. So if you bump into this torque limitation line, it means that yeah, your engine can no longer provide like the nominal power which is up here. It's in a way it's going like uphill in 5th gear without being able to shift gear on your car. You really want to do something here. The propeller is totally overloaded, but with a fixed drive and no CP propeller, you can't do anything about it. So in this case, you won't get out the nominal power. Now I've plotted the required power values for the 3 example spectra into this diagram. The points 1, 2, and 3 here. And there's also a point 2A, which is a pessimistic or conservative variation of point 2, and the optimistic point 2 variation here. We can now compare this to the characteristics of 2 different engines. First of all, we've got the green engine here, this one, which is a typical VLCC engine. It would bring the KVLCC2 up to about 15.5 knots in calm water with the usual C margin of 15%. And now then there's a little red engine here, which is smaller. It's about 12 megawatts MCR, and it brings the ship to about 12.2 knots in calm water with the same C margin. So you could consider this as the sort of slow steaming option of an engine. Now, as you see, the larger engine will deal without any problems with all the situations that the ship might encounter under the IMO adverse conditions, because all the points here, they're all well inside the green area here. But things are different for the smaller engine. Here, an optimistic choice of thrusted action factor, like the 2B point here, would bring us inside the red envelope here. Whereas if we choose thrusted action wake fraction pessimistically, we would just end up outside this area. So this does have a significant influence on results. So yeah, this it's important that you get the T's and W right, and the IMO guideline as it is not really clear about how you should determine it. So I think there's some room for improvement there. And this really brings me to the conclusions of my talk. We've seen that the level 1 assessment from the IMO guideline gives us a minimum power of 25.5 megawatts. If we follow this more advanced level 2 assessment, including the power prediction and so on, this power reduces to 12 megawatts. This is the red engine from the previous slide, which had an MCR of 12 megawatts. We've seen that it's important to consider those torque limitations for diesel engines because the propeller is highly loaded, is really overloaded in those conditions and operates far away from its design point. Those 12 megawatts from the pure power prediction, there were 9 initially, but we needed to choose 12 in order to not bump into the torque limitation of the engine. So it's important to consider this. Then an analysis of the resistance component shows that the total resistance consists of about 10% car water resistance, 24 wind, and 66 added resistance in waves. So RAW is really the dominating part here, and it's important to predict this correctly. The IMO guideline unfortunately neither specified details of how this should be determined experimentally, nor does it give a generic way to determine it. This is different from the car water and wind resistance components, where you also had like a generic main parameter based equation, but it's totally missing for added resistance. Then, because of the low test speeds of about 4 knots and the issue of tank wall reflections, it's important to carry out such tests in a wide basin, not in a narrow tank. You get reflection from the sides. The choice, finally, the choice of thrust adduction factor and wake fraction also is not very well defined in the guideline, but it has a huge influence on the outcome. And our suggestions are really like to carry out more research on this and start a discussion to plug those loopholes, because we've seen like shipyards trying to use the T and W really to save their ship, to make installation of small engines possible. So this was really all from my side today. Thanks for your attention.